the crystal structure of metals, diffusion of metals. Today we are going to talk about mechanical properties of metals. And here are today's objectives. As I said, we want to talk about mechanical properties. Uh, Today we will talk about the following things. And first, um, I want to introduce that. I want to tell you that mechanical behavior of a material it reflects the microscopic relationship between its response or deformation to applied load or force. That means you have the load first, or loads, multiple multiple loads. Then this is material and will um, respond to the loading conditions. And we want to understand the following concepts. First, we talk about stress and strain. And what are they, and why are they used instead of load and deformation? And elastic behavior. We have heard a lot of elasticity. What is elasticity? And what is elastic behavior? When elastic behavior means that when the loads are small, or when the loads are small, and the material deforms, and then if you remove the load, the material will recover its original shape and size. This is called elastic. So we will talk about when loads are small, how much deformation occurs, and what materials deform least. And plastic behavior. And plastic behavior is opposite to elastic behavior. Plastic behavior means that after you apply load, the material responds to the applied load, and then even after you remove the load, this material deformed already, and some deformation is permanent, cannot be recovered to the original size or the shape. So this is called plastic behavior. And then we talk about what materials are most resistant to permanent deformation. And then we talk about toughness and ductility. Toughness and ductility, what are they and how do we measure them? So as a mechanical engineer, how can we measure the toughness and ductility? So first we talk about elastic deformation. At the very beginning, here is a specimen. Here's a specimen. At the very beginning, initially we have this kind of atom arrangement. You can see here, and the small load, I guess kind of small load stretch. Suppose we have a tensile loading F. We stretch it. You can see the space between these rows, different rows, becomes larger. So this is a bond stretch. The bond, and among these atoms, there is a bond. Then you can see bonds the stretch. And if you remove the load F, and so this is a specimen and recovers its original size and original shape, and come here, return to the initial. So this one, and graphically we can use this diagram to show. So here is the delta. This is F. Okay, F. If you have F and you will have delta, loading condition is the cause, and F delta is the result. So if you have F, you have one delta, the displacement delta, and then when after you remove this F, and the deformation recovers, so the shape and size recover, and you can get this initial or recover the initial shape and size. So this is called elastic. Elastic means that reversible. Reversible means that if you remove the load after the deformation, and then the deformed the specimen will recover its original shape and size. This is reversible. On the contrary, nonlinear material, this is nonlinear elastic. There is a linear elastic, and there is some nonlinear elastic. Nonlinear elastic, as the name suggests, it is elastic. That means After you remove the load, so this specimen can recover its size and shape, but the relationship between F and delta is not a linear function. It is a curve. It is the general curve. You can see, go here, I remove the load, I keep increasing the load, and delta increases. Then I remove the load, it goes back, but it will goes back to the original shape along a curve instead of the straight line. So this is the difference between linear inelastic and nonlinear inelastic. Any questions so far? No question. And we talk about the plastic deformation, which is contrary to elastic deformation. So initially we have this atomic arrangement, and then with small load, and we have this small load, the bond strength and planes shear. This is planes shear. We have shear, and the planes shear we will generate the plastic deformation. Bond strength and results in the elastic deformation. And then after we remove the load, and so this specimen comes back, but not fully. Can it come here? And here, this is original length, but here is the final length. So this one will be the plastic deformation. If we compare this slide with the previous slide, we know that plastic deformation cannot be recovered. So this plastic means the permanent. And if we use this diagram to illustrate, you can see F, this is delta, linear inelastic goes here at the very beginning to here, right? And then here's a hardening here, F, go there, this curve. And then at this point, you remove the load. After you remove the load, so this specimen will go along these parts. So the slope of this straight line and the slope of this straight line are the same, right? Are the same. Young's modulus. This is are the same. This is we will not say Young's modulus. They are the slope the same. However, from here to here, you can see after you fully remove the load, and you can still have a delta here, and so this is a plastic. This is plastic deformation delta. Any questions so far? And you can see plastic deformation results from the plane shear. Okay, plane. If we have the plane shear, and we will have plastic deformation. You can see this microstructure determines the mechanical property. And then we talk about a very important the concept annealing stress. So this is infinitesimally small cube. If we have FT here, and we know the area of this cross-section, and we know that we can define the sigma as FT divided by A0. And so this one, it has the unit of pound force per square inch or Newton per square meter. So this is the English unit, and so this is the international unit. So keep in mind here, this annealing stress, so this is A is original area before loading. And why I emphasize this one, because as we extend the specimen, the instantaneous cross-sectional area A and keeps decreasing. And that will result in another the stress concept called true stress. And we will talk about the concept of true stress later. So this is the A0 here. We told you A0 here. This defines annealing stress. So this is the normal stress, sigma. And also we can have the shear stress and also use the same infinitesimally small cube here. So this is the cross-sectional area A0. If we have F here, okay, if we have F here, Fs, the shear force, and this shear force divided by the A0 will result in the shear stress tau. And you can see sigma and tau and they have the same unit. Either you can use either English unit or this is international unit. Questions so far? No question? And then we talk about the common states of the stress. And so here is a ski lift. There is a ski lift. And simple tension, the cable, the cable for simple tension. This is a cable, and we have F at this end, and this F at this is the left end. A0 is cross-sectional area, and sigma equals F divided by A0. You can see we have stress based on force. We get the stress here. So this is a tension, torsional. This is a torsion, a form of shear, for example, this is the drive shaft. When this guy is rotating, this drive shaft is experiencing the torsion. You can see experiencing a torsion. So here is this torsional moment M. Okay, torsional moment M, and the diameter equals 2r. R is radius. This is this AC here. And so here you can see we have Fs shear force, A0, and tau will be defined as Fs divided by A0. So you can see this tau is a shear force. You should know that, okay? Sigma denotes the normal stress, which is perpendicular to the cross-section area, and tau denotes the shear stress, which is parallel to the cross-sectional area. You should be very, very clear about these two concepts. So other common stress state. For this one, the simple compression, we have a boulder on the top. Here, this A0 compression, sigma equals F divided by A0. For this is the bridge for this beam, supporting beam, and we also have this is the loading condition, load compression, compressive loading, F divided by the area, cross-sectional area, we can have compressive the stress. So keep in mind, compressive stress is less than 0. And other common stress states. And here is a biaxial tension. So this pressurizes the tank. And we can see this is a infinitesimally small cube. So we have this sigma along the theta direction, this along the z direction. So this is a biaxial tension. And for here, so for example, this fish is swimming in the pond, right? So this guy experiences the hydrostatic compression. Do you know what is hydrostatic stress? Hydrostatic stress is under the water, and all these stresses from different directions remain the same for this given generic point. Then we talk about engineering strain. This is another important concept in mechanics and in mechanical engineering discipline. So tensile strain, we have tensile strain equals the displacement divided by the original length divided by original length. The shear strain is the shear angle gamma, and gamma equals, so this one plus this one. So this is gamma. Gamma here, we can write the gamma by using delta x divided by y. Okay. So this is if this is equals tangent theta, if the theta value is very, very small. Be very, very careful. And I'm going to teach offer the computer-aided engineering course. In that course, and I will give you the detailed derivation of these strain components. But here, for material science, we focus on the material properties based on the atomic arrangements of this material. So we will not focus on how we derive this shear strain and this tensile strain. But as I said, if you want to have the detailed information about these concepts, you can take another course, computer-aided engineering, in which I focus on the mechanics of elasticity. And so this will be very, very useful course as well. And one thing you need to keep in mind is that the string is always dimensionless. The string does not have dimension, does not have unit. Tensile string, shear string, and lateral string. And then we talk about the stress string, the testing. If you have taken mechanics of solids lab, excuse me, you might have already finished the stress strain testing for 3 materials: cast iron, these steel, along with this aluminum. As you can see, for 3 different metals and how they break differently. So here is a stress strain tensile machine. So here is the extensometer to measure the elongation of the specimen. This moving crosshead. So this load cell is used to calculate the force applied on the specimen. So typical tensile, because this is a tensile specimen here. So this end and this end are used to for the gripping purpose using the machine. Right. So here's a gauge length, and here's the gauge length, and we are going to measure the original length of this gauge length, and also use this extensometer to measure the elongation of this gauge length, and as the loading condition, as the load increases. Then we talk about linear elastic properties. Modulus of elasticity, Young's modulus, you also know Young's modulus, and Hooke's law. This is sigma and E. The relationship of sigma and E for linear elastic material can be written using this equation: sigma equals E. Right? This is the one-dimensional, the Hooke's law. The Hooke's law relates the stress to the strain, establish the relationship between the stress and the strain. This is a simple tensile test. So this is a square. This one, right? This one is original shape. So this one is the final shape. You can see if this specimen elongates around in vertical direction, in horizontal direction, this guy shrinks. So this is this you should need to know that, right? So Poisson's ratio. This is Poisson's ratio. You can see, and this is nu, is defined as epsilon L. This is epsilon L, and divided by the epsilon, right? So you have 2 directions, and one is longitudinal, one is transverse. So you need to know this. So why is we put a minus sign here? And because based on the configuration I just introduced, if in one direction there's a tensile stress, the tensile loading, in one direction it elongates, in another direction, and this specimen shrinks. So that's the reason we have a negative sign here. For the commonly used materials, metals, nu is about 0.33, ceramics about 1/4, polymers is about 40. And units, nu is dimensionless. I should know that. You can see because the nu is a ratio of longitudinal strain, and this is transverse strain. So Young's modulus is gigapascal or psi. Usually we use KSI. You can see when nu is greater than 0.5, the density increases. When nu is greater than 0.5, density decreases. The voids form. And so this is for some special materials. Then we talk about the mechanical properties. The slope of stress strain plot. Slope. This is the force. So this is a separation. Right? So this is a weakly bound. So this is a strongly bound. Depends on the bond strength of the metal. It is you can see this one is very df dr is very high, right? Very high. This one is lower because this guy has weakly bonded strength. Other elastic properties. The elastic shear modulus G, and G relates the shear strain and to the shear stress. Elastic bulk modulus K is related to volume. You can see here. Okay, so you have a P is all the P in the same direction. If compress it, pressure, the test, and so this volume changes, and so this is P equals negative K multiplied by delta V, the change of the volume divided by this original volume. And this is a negative sign here also because if the P pressure, okay, so if the pressure is negative and delta V, if the pressure, okay, so this is a pressure here, this is a pressure, delta V, this is a delta V here, delta V V0. So special relations for the isotropic materials, and G isotropic material means that this material for any given generic point, the mechanical properties are identical in all directions. So this is called isotropic material. G and E, they are related using this equation. And this is bulk modulus K and E they are related using this equation. Then we take a look at the Young's modulus, comparison of Young's modulus for this commonly used material. So this is gigapascal. Okay, giga is very high. G means 10 power 9. So usually you can see metals, alloys, and they have very high Young's modulus. Graphite, ceramic, semiconductor, this have a wider range because graphite has a relatively low Young's modulus. However, diamond they usually have a very high Young's modulus. The polymer is usually very low because polymer is very easy to deform. And composites and fibers, and they have a very wide range because composites and the mechanical properties of composites they are dependent upon what are the basic materials and how they are combined together. So here are useful linear elastic relationship for simple tension and for this simple torsion. So delta F force, L0 original length, A0 original this cross-sectional area, E is Young's modulus, and delta L you can see this is delta L. This is in another direction, right? In another direction. So here is FW0EA. So this is a simple torsion. This is a torsional. If you have this is a rotational moment, you can have an angle of twist. This is a rotational moment, also called the twisting moment. So this alpha equals 2 pi L0 and pi R04, and G is a shear modulus. Material geometric and loading parameters all contribute to deflection. And large elastic module minimize elastic deflection. And we know that, right? So this is large Young's modulus means that it is difficult to bend, difficult to elongate or shrink. And then we look at the plastic deformation. Plastic deformation, you can see simple tensile the testing. Engineering strain, we have sigma, and engineering strain epsilon. We go this way, loading load, and then before it's used, we can come back, recover the original shape and size. And however, at this point, if we keep applying the load, increase the load, and we go here, if we come here, then we remove the load, and the material will not recover along this original path. But however, instead they will go along this new path. So this one slope of this straight line and the slope of this straight line, and they are the same. So this is be very careful. Macroscopically, we can see why we have plastic deformation here, because we have this is slip planes here. The slip occurs among planes. So this is at this point, that means from 0 to 0. So this we call this delta epsilon p, the plastic strain. Plastic of the load is removed at low temperature. When this is operating temperature is less than 1/3 of melting temperature. So this one happens. The yield strength. I mentioned the yield strength. Yield strength means that if you the stress is bigger than the yield strength, the material is going to have plastic deformation. Look at here, yield strength. Go there, yield tensile strength, yield strength, then engineering strain. Yield strength. This is materials property. Right? Yield strength for different materials. We can see the metal. We have very wide range. We know that some materials are very easy to yield. Some materials are very difficult to yield. And also here is hard to measure for the ceramic and semiconductor. Polymer is low. Composite is also hard to measure also. And then we see VMSE. So this is the tool is very useful. And as I said, if you have bought the book and you have access to this resource, so using this VMSE, you can see the animation of this is how this specimen separates, how this one breaks, and then how you get this curve. Then we talk about tensile strength. And there are two very similar the words. One is a stress, S-T-R-E-S-S. Another one is called strength, S-T-R-E-N-G-T-H. The strength is the material parameter. Stress is the response of material, the stress level. You need to be very careful. So this is a tensile testing here. Engineering stress from 0 to here, the straight line. Then go to the tensile strength is the highest. Sometimes we also call this ultimate strength. This is highest point. Then it have this is necking and then the break, right? So this is a metal occurs when noticeable necking starts. Polymer occurs when polymer backbone chains are aligned and about to break. So here is a F fracture or ultimate strength. Ultimate strength, the fracture strength. Ultimate strength is here, and so this is usually this ultimate strength. People use this one as ultimate strength, but some authors they use different terms. So be very careful. Right? You need to know some other people use this is the highest point as ultimate strength. This is neck and material necks. We can neck. We can imagine what necking means, right? Neck is for our human body. Neck is the thinnest point, and so you can see very intuitively necking here means that, so there is a very thin part. This tensile testing results in very thin cross-sectional area. So this is called necking. Then we call about tensile strength comparison. So these are metal, alloys, ceramic, polymer, and also composites. Composite. They have a very huge, very wide range because, as I said, composites are very complicated, and because their properties are dependent upon what materials you are using and how they are arranged, how they are combined together. Ductility, we can see ductility. Plastic strength, strain, and failure. It is plastic, the tensile strain, and failure. Right. So here, annealing tensile stress. This is the ordinate. Annealing tensile strain. This is the epicenter. So this is L0 original length. So this LF at this LF, this length at this length it breaks. So this is ductility can be quantified using this equation, LF minus L0 divided by L0 multiplied by 100. Another ductility measurement using the change of cross-sectional area. So this is original cross-sectional area A0 and the final fracture area, cross-sectional area, and divided the difference between these two guys divided by A0, then multiply 100. So this one is another way to quantify the ductility. The toughness. Toughness, it means the energy needed to break a unit volume of material. And this is approximated by the area and the stress strain curve. Right? So at this point it breaks. So this is, we can just do the integration to get the area of this curve. For here, I'm using tensile strain for this material, right? So this pink area is this guy's the toughness. For this second material, so this is material, total material underneath this curve is this guy's toughness. And the same thing for this one, and the total material underneath this curve is called toughness of this material. We can see that this guy small toughness. This usually is the ceramics and brittle material, and it is very easy to break. So brittle fracture, elastic energy, almost elastic energy. Ductile fracture and contains elastic and plastic energy. For this one, it's very small toughness. Usually is unreinforced polymer. Resilience. So this is resilience. This is another very important concept. Ability to measure of a material to store energy. Energy stored best in elastic region, right? In elastic region. Resilience is, for suppose this is the stress strain, the curve. Resilience is defined as the area of this curve from origin to this yield strength. So this area is called resilience. All right, so this is the strain energy. This is strain energy density. If we assume a linear stress strain curve, this can be simplified as using this equation. Questions so far? No question? No question. We move on to elastic strain recovery. So this is a load. Loading goes here. This is a strain hardening, and then you remove the load and go to unloading. So this is elastic strain because it can be recovered. However, from the origin to this point, it is the plastic strain, which cannot be recovered. If you, at this point, if you reapply a load, and the loading parts will go along these parts, then come here and continue. And then we talk about this is hardness. And hardness is used to measure how difficult it is to indent the material. And there are several different hardness measurement systems. One is called Rockwell. In our mechanical engineering lab, and I teach students on how to do the hardness testing. That is, we are using Rockwell, the hardness testing tester. And we also have 3 skills, and we use HRC. And I think if you have taken mechanics engineering lab, you might have heard HRC. HRC means H is hardness, R is Rockwell, and C is a C skill. And C skill means that the major load, and we have 150 the kilogram. Okay, so this is A skill, we use a diamond. And B skill, we use 1/16 in the bore, and C we use a diamond. But here is the major load here. HB is a second commonly used hardness measurement system. It's called Brinell hardness. Brinell hardness is a tensile strength, tensile PSI, tensile strength MSI, MPascal. So this is international unit. This is international English unit. So here is we have a approximate relationship between TS and HB, and this for this unit system we have 500 as a factor. For this international unit system, we have 3.45 as a factor. And so this table shows the details of difference between the different hardness measuring system. We talk about Hartwell, we talk about Brinell, and here we also introduce the Vickers micro hardness and the Knoop micro hardness. So both of these two guys are for micro hardness measurement. As you can see, indenter for this whisker, for Vickers and Knooper, and we have diamond pyramid. For this is the shape of indentation, and we have side view and top view. So this is a Knoop, and so this is a Vickers. So this is a Rockwell, and this is a load PPP, and also formula for hardness numbers HB, HV, and HK, and all these things. You should know that. Okay, the baseline is that we have 4 different hardness the measurement systems. We have Rockwell, we have Brinell, we have Vickers. The fourth one is Knoop. So the third one and fourth one, they are used for micro hardness. And any questions? No question? So hardness observations. We give the hardness observations here. Hardness is a measure of material's resistance to localize the plastic deformation. We have indenter here. We just apply the indenter and to see how easy it is, and to have resistance, and then you can measure it. Okay. So the 2 most commonly hardness testing techniques are Rockwell and Brinell. And several skills are available for the Rockwell test. We know ABC. And as I said, if you are going to take a mechanical engineering lab, or you have taken, you should, if you have taken Rockwell mechanical engineering lab, Rockwell test. We have 3 skills, A, B, C. And if you are going to take mechanics engineering lab, you will learn how to use this machine, hardness testing machine. For the Brinell test, there is a single skill. One thing I want to mention is that we also often hear some pencils, they have different HB number. That is Brinell hardness. Right? So Brinell hardness is determined from indentation size, The Rockwell test is based on the difference in indentation depth from the imposition of minor and major loads. So these two harness measuring systems, they are performed based on different principles. The two micro indentation harness testing techniques are the Knoop and Vickers. Small indenters, and relatively light load are employed for these two techniques. They are used to measure the hardness of brittle material, such as ceramics, and also a very small specimen region. So for some metals, a plot of hardness versus tensile strength is linear. A plot of hardness versus tensile strength is linear. You need to know that, okay? That is, these two parameters are proportional to one another. Hardness, tensile strength, they have relatively linear relationship. Why? Because indentation can also be treated as a special form of deformation. Tensile strength is the measurement for the specimen to resist the tensile loading. And so that's the reason for metals. I'm talking about metals, hardness versus tensile, and they have a relatively linear relationship. And be very, very careful about this observation. The true stress and the strain. We talk about engineering stress and engineering strain, and then we talk about the true stress and true strain. How they are different from engineering counterparts. For true stress, okay? So true stress is equals F divided by AI. AI here is instantaneous cross-sectional area of the specimen, because when you do the tensile test, the specimen's cross-sectional area is changing, it's decreasing, right? So here it's called true stress. For true stress, it keeps increasing. And the true strain is a log of the ratio between Li, instantaneous length of the specimen, divided by the original length, L0. And also sigma t can be the true stress, true strain, how they are related to the engineering stress, engineering strain can be described using these two equations. What? Hardening. And hardening increase in yield strength due to plastic deformation. So here is one material, large deformation. Here is a small hardening. This is a large hardening. And curve fit to the stress strain. This is a response. This is sigma t, the true stress, equals k epsilon t n. So this is a hardening exponent. And n equals 0.5 some steels, n equals 0.5, 0.15 some steels, while n equals 0.5 some coppers. This is a true strain. So this equation is very, very similar to the equation for this is the creep testing, right? But that is sigma, that's for the sigma, increment of sigma, increment of epsilon. But here is the sigma and epsilon. Variability in materials parameter properties. We know that for same set of same, the bunch of same purchase of materials. So these materials, they have, even though they have nominally the same mechanical properties, but actually when we measure their mechanical properties, they are different from one another. So that's the reason we introduce the variability in mechanical properties. Elastic modulus is material property. Critical properties depend largely on sample flaws, defects, etc. Large sample to sample variability. We use a statistical tool to quantify the stress, the mechanical properties. So first, mean value, okay? So standard deviation. We will know mean value and standard deviation. So then we talk about design of safety factor. We have heard this one before. So here is design of safety factor, sigma working. Okay? So this is sigma ny, the yield strength divided by n. So we use the safety factor needs to be greater than 1. Okay. So this is why we call safety factor, because we do not want the n to be 1. That means for this case, physically, we don't want to use the operating stress to be exactly the same as sigma y. If this case, it's very, very dangerous. Sigma y, suppose we use the safety factor 5, that means we are very, very conservative. We can calculate sigma working. So summary, in today's class, we talk about the stress and strain, and these are size-dependent measures of load and displacement, respectively. Size, the stress and strain. Elastic behavior, that means after you remove the load, the deformation can be, the mechanical specimen can recover its original size and original shape. Plastic behavior means that after you remove the load, this plastic deformation some deformation cannot be recovered. The toughness, the energy needed to break a unit volume or material. Ductility, the plastic strain at failure.